readings. And this, again, is made possible by the fact that the East India Company and subsequently the British, as the colonial empire as a whole, collected this data over very large areas, recorded it, transmitted it among itself, within itself, so that this pattern could even become visible at all. Davis also points out that it was not long before this that the world's meteorologists agreed on a standardized way of measuring and reporting things like barometric pressure, so that you could have confidence that you were comparing similar things across different places. The initial theory that was offered to explain these things was sunspot theory. An 11-year oscillating cycle of activity on the sun. Now, and here's a picture. These are sunspots. This is the size of the Earth, just to give you a sense of the scale involved. These things have been observable features on the surface of the sun for a long time. And I think it was in the 1850s that somebody observed that they cycle, that the number of sunspots predictably cycles up and down on an 11-year periodicity. And this insight, discovery from astronomy, had enormous life. It had legs. It traveled. It persisted. People in all sorts of different fields thought that this represented a really key discovery for understanding things like not just weather, but ultimately also things like the economy. Believe it or not. If you looked at the work of Frederick Clements, very important ecologist, as late as the 1920s, he was attributing the cycle of droughts in the world's semi-arid grasslands to sunspots. He was convinced that this was the way to understand these cycles. Nowadays, it's considered one of these more or less discredited and dead theories because it doesn't hold up to scrutiny, but we'll get to that. So anyway, Norman Lockyer, who was an editor at Nature and a very prominent figure in the English-speaking scientific world, was very excited about this sunspot discovery, this cycle. He wrote, "The riddle of the probable times of occurrence of Indian famines has now been read, and they can be for the future accurately predicted, though not yet in various regions. The Nile River failures follow the same law." Stanley Jevons, whom we met last time when I happened to talk about Jevons' paradox, was an economist, a very important economist of the late 19th century in England, and he extended sunspot theory to explain global economic cycles. He said when it rains more during one end of this sunspot cycle, it rains more in China and India, which results in better crop yields, greater production, which means that for the time being, food is cheap, and the peasants can buy their food more easily, and they have a little bit of money left over. And he says they only need to have a little bit each because there's so many hundreds of millions of them that when you add that all up, it represents a significant amount of disposable income, which means that they buy more goods imported from Great Britain, industrial goods, which causes a sort of speculative burst of activity in the UK. And capitalists there ramp up production. They push their factories harder. They build new factories. They get very excited, which leads to greater production of these goods. But then when the sunspot cycle turns around the other way and rain fails in China and India, you have too many goods in the industrial sector and the global economy collapses. And Jevons was very excited about this and kept pushing the idea right up to his death, even as the empirical support for it became more and more difficult to sustain. One of the problems with this was that increased sunspot activity seemed to have inconsistent effects on rainfall depending on where you were. Sometimes it would appear to increase rainfall. Other times it would correlate with decreased rainfall. There were also problems in terms of the sequencing. Sometimes you would notice that, in fact, the sunspots increased after the rainfall fell or increased rather than before, suggesting that they couldn't be causally connected. Now, Davis makes a big deal out of this. For what reason? He suggests that this was motivated by the larger need of the British imperial system to deflect attention away from its own responsibility for the famines. That this was a way of suggesting that the British and their policies were not responsible for famine, that famine was simply the natural result of this sunspot oscillation that no one could control, and therefore this was a way of naturalizing the injustices of colonial rule. Davis makes a great deal of the idea that that's what's sort of going on here. There's an ideological need undergirding the popularity of these theories for people like Lockyer and Jevons. So Sir Gilbert Walker has his name on Walker circulation, which we'll get to in a moment. And he got that name given to it in his honor because of the work he had done early in the 20th century. He gathered enormous amounts of weather data from around the world, and he crunched it. He actually had people manually do the regressions because, of course, there weren't computers to do them for him. He employed literally thousands of Indians, actually, around the time of World War I to process all of this data. He had the statistical tools, but he didn't have the computational tools. It had to be done manually. It took years and years and years and years to try to tease out these patterns. And he identified, ultimately, what's now called the Southern Oscillation, which is the barometric seesaw over the equatorial Pacific Ocean. So the movement back and forth of high pressure and low pressure areas in the Pacific. This was correlated with the monsoon, but it was a poor predictor of it. He was, again, the goal here, in many ways, was to find predictive power, right? Was to be able to anticipate and predict the monsoon and whether it would fail. That was what everyone was hoping to find. And he found these patterns, which seemed to be explanatory in one sense, but they did not fulfill the need of coming up with some way of predicting this stuff. And the result was that this question, this scientific question, sort of fell out of favor as far as active research work for about 30 years. And didn't get sort of sorted out until later when more pieces were put together of this puzzle. So here's a depiction of El Nino and non-El Nino conditions in terms of pressure, barometric pressure. Notice here, the trade winds are driven by differences in barometric pressure away from high pressure zones towards low pressure zones. So this pattern in the normal circumstances drives the trade winds to push the surface of the ocean, the warm waters on the surface of the equatorial Pacific to the west and generate the sort of normal state of affairs that we looked at a moment ago. During an El Nino, what happens is that this high pressure, low pressure system is reversed, and the warm water here is no longer pushed eastward by the trade winds and actually begins to slosh back towards the middle of the Pacific. And meanwhile, the movement, the upwelling declines and water warms up over here. Now, the Walker circulation refers to these large cells that, and this is part of why, well, God, I don't want to go there. I don't understand climatology well enough to explain this in detail, and I'm not asking you to understand the mechanics of it, just to see the patterns. So here we have there's something about this that really seems very dramatic, huh? Given that this is the normal state of affairs. So the discovery of ENSO doesn't actually happen until the 1960s, when Jakob Bjerknes at UCLA figures out that the two things are linked. The change in sea surface temperatures and the change in barometric pressures are two manifestations of the same coupled system between the ocean and the atmosphere. And it's all about mediating solar energy, redistributing solar energy. So you get a chain reaction or positive feedback between winds, pressure, and sea surface temperatures that are self-generating and self-sustaining in each direction. Now, if you want to read more about this, the page numbers are up here for the chapter from Davis in which he discusses this. The point is, again, that we now know a great deal more about this and how it works, but we still don't know how to predict it with a great deal of confidence. George Philander in the 1980s identifies La Nina, which is the opposite of this oscillation. Klaus Wierke in Hawaii identifies the mechanism in ocean physics that links these two together. We still don't know what causes what, whether the ocean causes the atmosphere to change or the atmosphere causes the oceans to change, the winds or the temperatures. These are phenomena that we just don't yet have the capacity to fully predict and explain. But the thermocline, this is Wierke's contribution. If you think of this as the Pacific Ocean as a whole, under a normal circumstance of the Walker circulation, blowing the trade winds east, you get warm water building up in the west, and the thermocline is this difference, this elevational gradient of temperature, meaning that this is what pulls the cold water up from below and creates this upwelling. The interaction of these two is such that when the Walker circulation changes and the warm pool sloshes over here, this thermocline flattens out, which causes the upwelling to slow down, and as a result, you can get a sort of reinforcing pattern, right? The warm water here, which flattens the thermocline as it's moving over here, also causes the upwelling to stop, which further warms the surface of the ocean. Whew, God. I encourage anyone who's interested in this to track down my colleague John Chang and talk to him about it because he knows this stuff in excruciating detail. But this is the mystery of El Nino Southern Oscillation. The complexities remain, as I've already suggested. It's a complex quasi-periodicity whose geography is subject to important reconfigurations over time. If you look at that earlier graph with the red and the blue cycles up and down, we see something like a 3 to 7 year periodicity back and forth of this oscillation, but it's not very reliable because it appears to be superimposed on other longer-term cycles that affect, say, the magnitude of those events. And the overall sort of behavior of the system is therefore not simply a 3 to 7 year back and forth. These slower cycles can increase or decrease El Nino effects. The effects can lead or lag the anomalies in sea surface temperatures, which is just to say, again, we don't know whether the sea surface temperatures happen first and then cause the atmospheric ones or the other way around. And we sometimes can't really distinguish between El Nino events, sort of put a beginning point and an end point on them because, again, it can slow down and then accelerate again. The multiplicity of interaction modes between ENSO, major circulation regimes, and other periodic variables further complicate this. We know, for instance, that it affects the Indian monsoon, but there are other variables affecting the monsoon that can perhaps override the El Nino effect in a given year. And some people see evidence in recent years of a decoupling of El Nino and the Indian monsoon, which may or may not be attributable to, say, climate change. The effect in China, as mentioned earlier, is to shift rainfall southward, resulting in drought in the north and flooding in the south, rather than an overall decrease in rainfall as a whole for China. Generally speaking, El Nino has been a boon to U.S. agriculture because it gives us additional rainfall in the parts of the U.S. that grow a lot of food, even as the rest of the world, or much of the rest of the world, is experiencing drought. So it's sort of perfect circumstances for U.S. farmers. If you look at the map of an El Nino effect, you get a great deal more moisture through the southern part of the central United States, whereas in a La Nina event, you tend to have drier conditions, which is to say, we like El Nino here in the U.S., and it certainly helps that it hurts other farmers if you're thinking about this strictly from an economic point of view. Here again, El Nino, you get generally greater rainfall than normal over much of the middle of the United States. In a La Nina event, things are not as extreme, but if anything, it tends to decrease in much of the Midwest and Southwest. I guess it increases a little bit here in the Southeast. So we know that El Nino explains at least 20% of summer rainfall variability in southeastern Africa. It explains 40% of interannual variability in the Nile Basin, 50% in East Africa, and there's some evidence that global warming may be increasing the strength of El Ninos, although this is disputed. At this point, any real strong claims about the effects of climate change on El Nino are at this point pretty preliminary or speculative. We're not really sure what to expect. Although if you start digging around on the web, you'll find plenty of people who are ready to offer theories or predictions in one direction or the other. There are a lot of problems with the data limitations for this. We don't have sophisticated measurements that we would need before 1957. We don't even have quantitative weather records from before about 1875. Before that, we're forced to work with much more qualitative data. Davis points out that at the time that Walker was crunching all of his numbers would suggest a much stronger El Nino than what you get if you have all the data up to the present day. Again, there's some other factors influencing the overall effect of El Nino, so that it appears it was particularly pronounced and extreme during that period of these famines in India in the late 19th century. In any case, this is not a puzzle that is solved completely at this point, and it's an active area of research. Let's go ahead and take a 5-minute break, and then we'll come back. Okay. So now that we understand El Nino, let's think about this in the context of imperialism and science and Davis's indictment of the activities of the British as a Holocaust. It's just to start out worth pointing out that without the imperial network of weather monitoring and data collection, we wouldn't even have been able to see El Nino Southern Oscillation. It would have been perhaps invisible to us. In that sense, the science of El Nino is actually itself dependent on imperialism, at least as a matter of just historical record. The science was mobilized for reasons other than simply the pursuit of knowledge itself, right? It was mobilized in reaction to economic issues of colonial productivity, which had effect on taxes and tariffs, revenues from trade. It had indirect effects on the well-being of the growing industrial plant of the United Kingdom itself, right? This had effects on whether you could make money in the factories of England as well as in the fields of India. This science also, according to Davis, naturalized famine as an ecological or climatological cycle rather than as a social issue. And this gets to those points I made a moment ago about the enthusiasm for sunspot theory. Davis points out that the very first person to notice these patterns blamed it on the effects of imperialism on local agricultural production, a social cause. The need, according to Davis, later on in the 19th century, was to find ways of explaining famine that made it look like the fault of the rainfall, or the fault of the gods, so to speak, rather than the fault of the British. The knowledge that was gained or was eventually gained may or may not help in the sense of remediating or reducing the negative impacts, right? The famines itself. Scientific objectivity in these cases is somewhat slippery, dependent on the status and reputation of individuals and institutions and their ability to persuade people in power that this information is accurate or gives them some tool that they should use in a different way. In other words, the story told by Davis is one in which science is always mediated by politics and economics in terms of what kinds of things are identified as problems or issues, in terms of what kinds of research gets funded, how those findings are disseminated, the personal or professional interests of the scientists themselves. These are also things that are frequently missing from the so-called literature about science itself. And this is also, this is why Davis feels the need to tell the story in terms of imperialism, rather than simply telling it as a story of scientific discovery and knowledge acquisition, right? He wants us to think about this sort of larger social context that affects what we learn, what we identify as knowledge, and these are things that frequently don't get written into the papers in climatological journals where the results are presented, okay? So the causes of El Nino holocausts. How did El Nino events, which had of course been going on for hundreds and perhaps thousands of years, translate into these acute mortality events in India and elsewhere?